assembly, you'll see that it's on slightly more. It's exactly 1/2. And then when you add them together, it's perfect. Now again, since this is a completely abstract implementation, it's the simulated blocks with these perfect dead zones and this perfect saturation, it gives you a perfect reconstruction when you add things back together. In reality, things aren't that way. So when you have your transistor and you have your tubes, you've got this overlap, the dead zone region. Like I said, it's more exponential. You've got the thing that maybe, 0.7 still has a little bit of crossover distortion. It's not perfectly turning out. So maybe you need to bias it at like 0.8 or 0.9. You need to turn it around. Similar with tubes, there's always this issue with biasing the output tubes. And that comes down to how much crossover distortion you get. Yeah, some people say, oh, you can just read the current and do it. And other people say, no, you got to look at the waveform. You got to look at how much crossover distortion you're getting. And then you look at the numbers to make sure you're not out of the safe range. Because if you have to go, to the point where you're conducting 70 or 80% to get rid of the crossover distortion, well, maybe you can limit some crossover distortion. Because it shouldn't, the Class A amp shouldn't be operating with 70 or 80% conduction. Class D. Now, Class D is a totally different implementation. The idea of Class D is what I said before. You only dissipate power when you're conducting. So let's say we don't conduct. We're either in saturation or we're in cutoff. Okay, well, great. How is that useful? And the answer is, well, you can reintegrate that and make it into an audio waveform. And it's, diabolically simple. It's a brilliant idea. The details of the implementation get kind of hairy. But it's worked out at this point now that it's very popular in certain devices. For instance, laptops almost always use Class D output amplifiers because they're very efficient. And now TI makes them, and other companies are making them, and they're available on a chip. And you put them in there, and you can get 6 watts, up to 20 watts pretty easily. To do higher power is possible, and most companies will sell a rack mount power amp that's Class D. Your QSCs, your Stewart power amps. You can find Class D amps, and they're smaller and lighter, but they're more expensive. The signal generator, again, here is a sinusoid. So we look at the sinusoid. The repeating sequence is, in effect, a kind of sampling waveform. It's a ramp waveform. And what we do is we compare our input signal to this ramp waveform. And this ramp waveform is actually operating at something like 50 to 100 kilohertz. It's above audio frequencies because it's kind of sampling. So you've got the same issue with the Nyquist rate. And then what we're doing is we're taking a hard threshold sign. So we're saying, compare the sampling waveform to the signal and give you one bit out, plus or minus. Is the signal greater than the repeating waveform at a given time? So this is going to give us out a PWM signal. And we'll see the curves on the next slide. That if it's high, it's usually, the input signal is usually above the repeating sequence. So we've got a wide pulse width. And if it's very low, the repeating sequence is most often higher than the input signal, so we get a very narrow repeating pulse width. And we'll see that next. Okay, so this talks about we get PWM. And again, key devices are not conducting all the time. Yeah, your input signal and any buffer, obviously there is conducting, the repeating sequence is conducting, but those are low power. Once you get to this sign, you do the high power here, and then you have the passive filter to give you back your signal, right? And so they're mostly using really high power PA amps. You can buy 800 watt Class D amps. So here's what it looks like. We take the input, and that looks kind of like the sinusoid, and we sample it, so we get this pulse width modulated signal. So here, you can kind of imagine the sinusoid in here. That here is at its lowest point, and then as it's going up here, we're getting to about 50% duty cycle, and as we get up to here, we're at 100% duty cycle, and then we kind of come back down again. You can see the ratio of the pulse width to the signal. And then, well, okay, I've got these pulses. How do I get back to a sine wave? If you just, if you were just presented this, how would you get back to a sine wave? By looking at that. Mathematically, how would you do it?
Mathematically?
Mathematically.
So the frequency components of it? Duty cycle?
Simpler than that. Yeah, duty cycle. So let's take a look at, think about, look at the duty cycle over each period, right? We said the duty cycle is relative to the amplitude of the input signal. So how do you go back from that? What do you do? Well, you're looking at the duty cycle. That's a sum, right? So what's a sum in analog terms?
Sum and analog.
Or what's the equivalent operation if you're doing? Sorry, sum is kind of a discrete time thing. It's a discrete quantity thing.
Right.
So integrals. So you integrate it, right? What was one of the things you learned when you did Laplace, right? 1 over s is an integrator. Well, how do you approximate 1 over s with components? You create a low-pass filter. So what we have here, I'm using an analog Butterworth low-pass filter. You can use any number of low-pass filters. But you take these high current pulses and you run them into a low-pass filter, that acts as an integrator. Out of that low-pass filter is an analog signal. And the nice thing about it, too, is that for a lot of these lower power amps, you don't actually have to use a separate low-pass filter because the speaker is a low-pass filter, right? If you think about like I think I mentioned the AM detector, the AM radio, you're doing the same thing. You're rectifying this AM radio signal, then you're running it through headphones or the speaker, and that acts as a low-pass filter. Same thing here. The speaker can act as a low-pass filter. All right, so now let's go briefly back to MATLAB, and I'll just show you these demos in real time. So start it up. Okay, so I'll open up the slider. That's our perfect sine wave. And that's the output. So the problem obviously is
Bias wrong.
Yep. So I think we can just bias it one time. Let's see. Pop in 50 there. Okay, bias is right, but
It was a little too high.
yeah, that's perfect. So that's a nice thing. I'm not a huge fan of Simulink. I've run into some problems with it in the past, but for stuff like this, I find it pretty useful. That it gives you a nice demo, and I can just go back and forth and control the gain and say, okay, where's my saturation? Or I can go back here, adjust the bias, and if I want to illustrate that asymmetric clipping, well, that's a nice way to demonstrate asymmetric clipping. We can also go in, the real one, we can go in and modify the saturation. The lower limit, you have to make the lower limit 20. Basically, bring up the ground level, if you will. And that'll give you even more extreme asymmetric clipping. So it's a really useful visualization tool. And if you have any interest, I can upload these models. They're pretty basic. I mean, you can create them yourself without much problem. Okay, so let me go back and stop class. Class A, class B. So again, with class B, we've got the top and the bottom separately. We add it together to get the crossover distortion. We can go into the dead zone. So yeah, so the dead zone is from minus infinity to 50.